anharmonic oscillator. So what we are going to do, we are going to assume that a diatomic molecule, okay, diatomic molecule behaves like an anharmonic oscillator. Right? Okay, what is an anharmonic oscillator? It is the behavior of real molecules, simple. Okay, anharmonic oscillators, right, for which if you plot potential energy versus the displacement, potential energy in x-axis and displacement, potential energy y-axis and displacement in x-axis, if you plot, suppose you take this as x equal to 0 and this side x is positive and this side x is negative. Okay, in the case of simple harmonic oscillator, right, potential energy is equal to kx square by 2, we know that, where x is nothing but displacement. Okay, so potential energy and x, that relation is a parabolic relation. So if you plot potential energy versus x, you will get a parabola. Okay, let me draw a parabola here. You will get a parabola in the case of diatomic molecule behaving like simple harmonic oscillator. If molecule behaves like simple harmonic oscillator, then potential energy versus displacement, okay, this plot will give you a parabola, right, and this parabola will go to any extent of vibration, right, any amplitude of vibration, right. But what actually happened in the case of real molecule? In the case of real molecule, right, if you stretch the molecule, see, x negative means compression, x positive means elongation. Elongation is also called stretching, right. If you stretch the molecule, okay, continuously, what will happen? After a particular extent of amplitude of vibration, the molecule will break, the bond will break. Okay, therefore the potential energy function for real molecule, for anharmonic oscillator is nothing but real molecule. Behavior of real molecule, okay, we say that it is anharmonic. So real molecules are anharmonic oscillators. Okay, in the case of anharmonic oscillators, right, the potential energy function, right, will go like this. The potential energy function will appear something like this, right. It is not parabolic. What is actually happening? If you stretch the bond, or if you elongate the bond, after a certain distance, what will happen? The potential energy become constant. That means the bond breaks. Okay, so this energy, the potential energy become constant, and this energy from 0 to this, we call this energy as equilibrium dissociation energy of the molecule. Okay, so this is the potential energy function for real molecule or anharmonic oscillator. Anharmonic oscillators, okay, supposed to have potential energy like this. Okay, that is, after a certain extent of vibration, after certain amplitude of vibration, or beyond certain amplitude of vibration, the bond will dissociate and you will get atoms. Okay, therefore the potential energy becomes the sum of the potential energies of the two atoms, which is a constant. Therefore potential energy become constant, right, after a certain elongation. Okay, this value is what we call as equilibrium dissociation energy of the molecule, right. The scientist MORSE, he introduced an empirical relation to fit with this curve. Okay, to fit with this curve, MORSE gave an equation. It is called MORSE potential energy function. MORSE potential energy function. It is just an empirical relation. In order to fit with this anharmonic oscillator curve, MORSE gave an equation like this. What is the equation? Potential energy V of x equal to equilibrium dissociation energy of the molecule into 1 minus e to the power minus ax whole square. This is the equation, where dE is nothing but, what is dE? dE is nothing but equilibrium dissociation energy of the molecule, okay, in joules. This is equilibrium dissociation energy molecule in joules, okay, so this is in joule, right? And what is A here? A is actually a parameter, or I can say in the other way it's a constant. A is a constant for a given molecule. For a given molecule. It is not a constant for all molecule. It is a constant for a given molecule. For another molecule, it will get another constant like that. Okay. And what is x? X is nothing but displacement. You know very well, x is nothing but L minus L naught. Okay. Where L naught is the equilibrium bond length and L is the bond length during vibration. Okay, during stretching, during elongation or compression. Right? Yeah, in elongation x will be positive and in compression x will be negative. Right? Now, if you expand this using a minus b whole square formula, and if you use the exponential expansion and all, right, you can write this expansion also as, let me write the next page, you can write like this also, v of x equal to equilibrium dissociation energy into a square x square minus a cube x cube plus etc etc, like that goes. Okay, this expansion we did in the last class. Okay, now I'm just writing the expansion directly, a square x square minus a cube x cube. Remember, a is a constant for a given molecule and x is the displacement. dE is nothing but equilibrium dissociation energy of the molecule. Okay, now see case, let me take case 1 here. Will this equation explains the required information? Okay, see, if x is small, what will happen? If x is very small, okay, x very small means the amplitude of vibration is very, very small. If amplitude of vibration is very small, see, when x is very small, then see here the blue line and the black line, right? There is a simple harmonic oscillator curve and the anharmonic oscillator curve. See here, see in this area, they merge, right? Simple harmonic oscillator curve and the anharmonic oscillator curve both merges there. So when x is very small, anharmonic oscillator or real molecule behaves like simple harmonic oscillator. No doubt in that, it's correct. So if x is very small, right, very small, in this case real molecules behave as simple harmonic oscillator. Real molecule behave like simple harmonic oscillator. Okay, so you know very well, for simple harmonic oscillator, potential energy equal to force constant k into x square by 2. This we know. And if I use this equation, see, if x is very, very small, okay, usually x value will be 0.01 or 0.1 like that. Okay, it should be less than 1, right? If x is small, then x cube and higher power terms, right? Higher power terms become very, very small. So these higher power terms become negligible. Okay, so I'll write that v of x equal to dE into a square x square minus a cube x cube plus etc. So this is the actual expansion. Okay, if x is very, very, very small, yeah, if x is very small, then these higher power terms become negligible. If I neglect these, then potential energy equal to equilibrium dissociation energy into a square minus x square, will get this. Okay, if the amplitude of vibration is very small, then real molecule behaves like simple harmonic oscillator. So the simple harmonic oscillation assumption is correct only for small amplitude of vibration. Okay, and we get the potential energy like this, and you know very well for simple harmonic oscillator potential energy is also equal to kx square by 2, right? So if I equate these two, what we get, kx square by 2 equal to dE a square x square. From this we can find the value of a square. See, x square you can cancel. So what is a square? Let me write in the next page. So what is a square here? A square equal to k, force constant k by 2 into equilibrium dissociation energy of the molecule, right? Then what is A? A is equal to square root of k by 2 into dE, right, where k is the force constant of the bond, dE is the equilibrium dissociation energy of the molecule. Okay, and we usually write this value. We will write this value, right, in terms of Sutherland parameter, okay, as delta square root of delta divided by the equilibrium bond length L naught. Students, observe carefully. What is delta? Delta is called Sutherland parameter. It is called Sutherland parameter, right? And what is delta? Delta is nothing but k L naught square divided by 2 into dE. K L naught square divided by 2 into dE, and this is what we call the Sutherland parameter. Okay, so here I have written A in terms of Sutherland parameter. So remember both this equation. These two are very, very important. Note down. Sometime in the examination or in CSIR examination, they may give the value of delta, Sutherland parameter. They may ask you to calculate the value of A. Okay, so A is nothing but Morse potential energy constant. Morse potential energy constant, or simply constant. Right, students, any doubt in this? Any doubt up to this? Okay, good. Yeah, so you can find the value of A by making use of this relation, right? Then what happens if x is very, very large? Okay, or I'll say that if I stretch the molecule to a larger extent, okay, if L is very much greater than L naught. L naught is the equilibrium bond length. L means L is nothing but, if L is greater than L naught, L value greater than L naught means we are stretching the bond, right? If you stretch the bond to very large extent, that is, x will approaches infinity, say, for example. Okay, because x is nothing but L minus L naught, right? If L is very, very high, very, very large, then L minus L naught will be very, very large. Or I can say that if x approaches infinity, what will happen? You know very well, potential energy V of x equal to equilibrium dissociation energy into 1 minus e power minus ax the whole square, correct? If I put x is equal to infinity here, okay, if I put infinity here, you will get e power minus infinity. E power minus infinity is 0. Therefore, we get e power minus infinity becomes 0. So we get whole square. 1 square is 1. So you'll get just d. Potential energy becomes equal to equilibrium dissociation energy when L become very large. Okay, if you stretch the bond to larger extent, the bond will break. Then potential energy become constant. That constant potential energy is nothing but the equilibrium dissociation energy of the molecule. Yes, Morse equation, okay, could explain the potential energy function for real molecule clearly, almost clearly. Okay, then if x is not too large, suppose if x is very, very small, a molecule will behave like simple harmonic oscillator. If x become very large, if x approaches to a very large value, then potential energy becomes equal to the equilibrium dissociation energy. If x is not very small, it's not very small, it is somewhat a higher value. If x is not very small, in this case potential energy V of x should be given as equilibrium dissociation energy into a square x square minus a cube x cube plus etc etc. This equation you have to use. Okay, and you know very well, I have given this definition already. What is force constant? Force constant is nothing but second derivative of potential energy with respect to displacement, d square by v by dx square at x equal to 0, correct? This is the definition of force constant, right? I have given this already. K is equal to d square v by dx square. Now we have expression for v. If I differentiate this 2 times and if I put x value equal to 0 in the final expression, I will get the force constant. Okay, so let me differentiate this once. dv by dx equal to, okay, what we get is dE into, if I differentiate this, I'll get 2a square x minus 3a cube x square plus etc etc, like that it goes. Okay, then if I differentiate second time, d square v by dx square, what we get, I'll keep this d as it's a constant, I'll keep it as it. If I differentiate x, it become 1, so I'll get 2a square. Then I'll get here, I'll get 6a cube x plus etc etc. Students, observe carefully here. All these terms contain x. All these terms contain x. This is the only term which does not contain x. Okay. So if you put x equal to 0, so d square v by dx square, if I put x equal to 0, what will happen? All these terms become 0. So what is left with? We left with only this 2a square into d. Okay, 2a square into d, and this is nothing but force constant. So k is equal to 2a square de. Take down, student. I got, see, we have obtained the same expression, right? Already I gave that. A is equal to square root of k by 2 into de. We got the same expression. You can get the expression in this manner also. Why I am giving this? Listen, even if x is not very small, see, even if x is not very small, force constant should be calculated using this, or a value should be calculated using this. That's the point. Don't think that only when x is very very small we should calculate a using this formula. No, even if x is not very small, you can calculate the value of a using this formula. Okay, now you know very well the equilibrium vibrational frequency omega e bar, or omega e bar equal to 1 by 2 pi c square root of force constant k by mu, right, for a diatomic molecule, right? Here I can write that omega e bar equal to 1 by 2 pi c, I'll keep all these terms as such, into square root of, in the place of k I'll put this 2a square equilibrium dissociation energy by mu, right? If I bring this 2 pi inside, it will become 4 pi square c. Okay, I'll bring all these terms inside, and if it stays square root of a square is a, so I'll keep a out. Students, take down this, make it fast. Is this clear, student? Any doubt? Now, students, any doubt?
No, sir.
Okay, right.
No, sir.
Take two. So I can write the expression for equilibrium vibrational frequency as, listen, omega e bar equal to, I'll bring this 2 pi c inside of square root, and I'll take it a square out. So square root of a square is a into square root of 2 dE by 2 square become 4 pi square c into mu. Okay. Now,
C square varada sir.
Pardon? Yes.
C square varada sir.
C square. Yes. Good. Very good. C square. See, you know very well h is equal to, sorry, h bar. What is h bar? H bar equal to h by 2 pi, or h bar square equal to h square by 4 pi square. Am I right? H square by 4 pi square. Is this clear, student? Hello?
Yes, sir.
This we know.
Yes, sir.
This we know already, right? Now, what I am going to do, I am going to substitute this value here. So in the place of 4 pi square, there is no mistake in that. We can write in terms of Planck constant. Okay, let me leave it as such. Omega e bar equal to a into square root of 2 dE, or you can cancel that 2 and 4, so we get dE by 2 pi square c square mu. Using this relation, we can calculate the equilibrium vibrational frequency of the bond. Okay, take note. Take note. So if you know, students, observe carefully, you can calculate A using this formula. If you know force constant and equilibrium dissociation energy, you can calculate A. If you know A and equilibrium dissociation energy and reduced mass of the molecule, yes, you can calculate equilibrium vibration frequency of the bond theoretically. Okay, take note. So this will give you the equilibrium vibrational frequency of the bond. Okay, take note. Is this clear, student? Any doubt? These are all some important relations you should keep in mind. Okay, now let me move further. So we have discussed about the Morse potential energy function, okay, and how the potential energy function will behave in the case of small amplitude of vibration, and if x become very large, what will happen, right? All those things we discussed. Now what I'm going to do, listen, the ultimate goal is that we need to solve the Schrodinger equation. So let me write the time independent Schrodinger equation, okay, for the anharmonic oscillator. So what's the equation? This is general form, h psi of x equal to E into psi of x. Okay, for one dimensional anharmonic oscillator I am going to write. What is h here? Hamiltonian is nothing but kinetic energy operator minus h bar square by 2 mu, okay, into d square by dx square. This is the kinetic energy operator in one dimension, plus potential energy. We have to put the Morse function. So I am going to derive, or I am going to solve the Schrodinger equation for Morse operator. I'm sorry, Morse oscillator. Morse oscillator. What is Morse oscillator? Oscillators which follow the Morse potential energy function. Students, observe carefully. Oscillators which follow or which obey Morse potential energy function is called Morse oscillator. So for Morse oscillator, potential energy formula is you know very well, equilibrium dissociation energy, right, into 1 minus e power minus ax the whole square, right, into psi of x equal to e into psi of x. So this is the equation we need to solve, right. This equation can be solved by using approximate methods. Okay, by using approximate method we can solve this, right, and we get the energy expression as like this: EV equal to EV, that is energy depends on vibrational quantum number V, which comes out as V plus half into hc omega e bar. This term you might have seen already, which is nothing but vibration energy for a simple harmonic oscillator. Okay, now you'll have other terms. Okay, the second term, that is V plus half the whole square, okay, into hc xe omega e bar. You'll get another term here. Okay, we have new term xe, right, omega e bar and all usual terms, right. So this is the vibration energy formula we get if you solve the Schrodinger equation, okay, using approximate methods. Okay, yeah, usually we follow perturbation theory. By using perturbation theory we can solve this, and if you solve it you will get this expression as energy. Okay, take down. This is energy in joules. Energy in joules. But I have told you already, in vibrational spectroscopy, right, in most cases, okay, we plot intensity in y-axis and wave number in x-axis. So if you have energy in wave number unit, it is better because you will get direct relation with the frequency of the radiation. Okay, so for our convenience we are going to write this vibration energy in terms of wave number, right. In terms of wave number we write vibration energy using the expression, using the notation GV. GV is nothing but vibrational energy in wave number unit, where V is the vibrational quantum number, okay, is equal to, what is vibration energy in wave number? Vibration energy in joule divided by hc, that we know. So you divide this by hc and this by hc, so hc cancel in both the terms. So what we get? What we get is that, let me write in the next page. What we get is that GV equal to V plus half into omega e bar minus V plus half the whole square into xe into omega e bar. Okay, this is the expression we get for vibrational energy in wave number unit. This is in wave number unit. Let me put centimeter inverse. Okay, it is in wave number unit, where V is called vibrational quantum number, which can take value 0, 1, 2, 3, 4, etc. Okay, and omega e bar is the equilibrium vibrational frequency of the bond. Equilibrium vibrational frequency of the bond. Vibrational frequency, right, and Xc is called the unharmonicity constant. Unharmonicity constant. Students, note down, it's very, very important. And remember, the value of Xc, right, for most cases will be in the range of 0.01. It is very, very small actually. Xc is called unharmonicity constant. For most molecule, the value comes out in the range of 0.01. Okay, take down. Students, is this clear? Any doubt? Any doubt after this? Hello?
Yes, sir.
Right? Yes, no doubt. And if I plot, okay, let me find the value of GV first for different vibration level. Okay, so if V equal to 0, it is called the ground vibrational state. For ground vibrational state, what is the energy? GV equal to G0 equal to, if you put V equal to 0, G0 equal to, so wherever V is there, you put 0. 0 plus half is half into omega E bar. Okay, so half into omega E bar here, minus. Then if you put V equal to 0 here, 0 plus 1 by 2 is 1 by 2. 1 by 2 square is 1 by 4. So you'll get 1 by 4 into Xe into omega E bar. Okay, actually this is the ground state energy for simple harmonic oscillator. For anharmonic oscillator, you must subtract this quantity from this value. So what happens? The actual the introduction of Morse potential energy function, okay, will reduce the vibrational energy of each state. Reduce the vibrational energy of each state. Okay, so in the potential energy plot, let me draw like this. This is potential energy, and here we have x. Here x equal to 0, and the potential energy function for real molecule will look something like this. I have drawn already, which will look like something like this, and this is the equilibrium dissociation energy of the molecule. Now listen, if I put V equal to 0, okay, if I put V equal to 0, then we'll get the lowest potential energy as this. Okay, our lowest energy of the molecule like this. Okay, so let me draw that separately. Okay, in the same diagram we'll do. See, we'll get the energy as the first energy like here. So this is the energy at V equal to 0. This is the ground vibrational state energy of the molecule. And what is the energy? The energy value is of omega E bar minus 1 by 4 Xe omega E bar. It is not 0. See, that's very important. It is not 0. Classically, the energy of the molecule, the lowest possible energy of the molecule is 0. But quantum mechanically, the energy is not 0. You'll get some value. In the case of anharmonic oscillator, the value is this. Okay, we call this value also as 0 point energy of the molecule. Okay, so this is nothing but 0 point energy of the molecule. What is 0 point energy? Very simple. Lowest energy possible, okay, in through quantum mechanical result, and lowest energy possible through classical result. Take the difference. The difference is nothing but 0 point energy. So here classically the lowest possible energy is 0, whereas quantum mechanically the lowest possible value of energy is this. So what is the difference? Difference is this. Therefore this is what we call as 0 point energy of the molecule. Now if I put V equal to 1, what will I get? Let me write here. V equal to 1. If I put V equal to 1, then G1 equal to, so wherever V is there, you put 1 here. 1 plus 1 by 2 is 3 by 2. So you'll get 3 by 2 omega E bar. Then minus, put 1 here, V equal to 1. 1 plus 1 by 2 is 3 by 2. 3 by 2 square is 9 by 4. 9 by 4 Xe into omega E bar. Okay, so depending upon the value of omega E, okay, you will get some value of energy. Let the energy be this. Okay, let the energy be this. So this is energy at V equal to 1. Right. Similarly, if V equal to 2, then G value equal to. So this curve indicate potential energy. This line indicate the total energy of the molecule. Okay, see, this is potential energy function. Potential energy function is continuous, but the total energy is not continuous, it is discontinuous. Okay, I'm just giving you total energy here. Student, be careful in that. Potential energy is appearing as a continuous function, but total energy is quantized. Okay, when V equal to 0, this is the energy. So this is the energy actually, V equal to 0. And when V equal to 1, this is the energy. Okay, between these two, there are many possible values are there, but those values are not accessible by the molecule, right? When V equal to 2, what will happen? If I put V equal to 2, put 2 here, 2 plus 1 by 2 is 5 by 2, so you'll get 5 by 2 omega E bar. I'll write here 5 by 2 omega E bar minus, here also if we put V equal to 2, 2 plus 1 by 2 is 5 by 2, 5 by 2 square is 25 by 4, 4 Xe into omega E bar. So this is the vibration energy when V equal to 2. So when V equal to 2, you'll get the vibration energy here. Okay, this is vibration energy when V equal to 2, right? Now students, observe carefully. If you see the gap between adjacent level, is the gap decreases or increases or remains constant? Okay, for that you need to find out what is the energy required or what is the energy gap between adjacent level. Okay, listen, the energy gap between adjacent level, let me do it in the next page. Students, observe carefully. Energy gap between adjacent level, that is delta G. Delta G adjacent, I'll put adjacent. Energy gap between adjacent level. How to do that? Energy of the vibration level, V plus 1 level, minus energy of the V level, correct? Because we are going to find the gap between adjacent level. So you know very well, if the lower level is V, the higher level should be V plus 1. Okay, so energy of the V plus 1 level minus energy of the V level will give you delta G. Okay, see how to find energy of the V plus 1 level? Very simple. Wherever V is there in the formula, in the energy formula, wherever V is there, you put V plus 1 here. So you will get V plus 1 means 3 by 2, it becomes 3 by 2. So V plus 3 by 2 omega E bar. I'll write here V plus 3 by 2 omega E bar. Then we have minus sign here. Then again put V plus 1 here, you'll get V plus 3 by 2 minus within bracket V plus 3 by 2 the whole square into Xc into omega E bar. This is the energy for V plus 1 level, correct? Minus what is the energy for Vth level? Okay, just write the formula as such. Okay, what is the formula? V plus half into omega E bar minus V plus half the whole square into Xc into omega E bar, right? Now I'll simplify this. V plus I'll multiply this with omega E bar. So what we get is V into omega E bar plus 3 by 2 omega E plus 3 by 2 omega E bar here, and here we get minus, let me write this once as such, V plus 3 by 2 whole square Xe omega E bar, and you will multiply this by minus, so you will get minus V into omega E bar, minus of plus become minus of omega E bar, then here minus of minus become plus V plus 1 by 2 the whole square into Xc into omega E bar. Observe this carefully, students. Observe this carefully. It's a very simple one. Okay, I'm not doing any big integration or differentiation. I'm just applying the simple mathematics. Okay, 8th standard mathematics. Right? Now here, this is plus V into omega E bar. This is minus V into omega E bar. They cancel. Then here we have plus 3 by 2 omega E bar. Here I have minus 1 by 2 omega. If I subtract, I'll get omega E bar. Okay, I'll get omega E bar. Then here we have minus V plus 3 by 2 whole square Xc omega E bar. Here we have plus V plus 3 by 2 whole square Xc omega E bar. I'll take minus as common. I'll take minus as common. Students, observe carefully. And I'll take Xc omega E bar as common. I'll keep it in this side, in the right hand side. And what is left with? Here we have V plus 3 by 2 whole square. I'll use A plus B whole square formula. So A square plus B square plus 2AB, 2 cancels, so we'll get 3V. Okay, if I expand this by A plus B whole square formula, I'll get this. If I expand this by A plus B whole square, I'll get A square, that is V square, but we have minus sign in front. So, okay, let me expand that once. Plus I'm sorry, I'll take minus as common, therefore this become minus, so you have to multiply by minus everywhere, right? I'm sorry. So minus a square minus 1 by 2 square is minus 1 by 4. Then we have v, minus v inside. Students, I did it directly. You do one thing, you take the square of this, use a plus b whole square formula here, a plus b whole square formula here, then subtract. Okay, you just do it in stepwise. Okay, I did directly. Anyway, plus v square minus v square cancel here. 3v minus v become 2v, right? So what we left with is omega e bar minus, here we have 2v, and plus 9 by 4 minus 1 by 4. If we subtract, denominator is same, therefore 9 minus 1 is 8, 8 by 4 is 2, so we'll get plus 2 into xc into omega e bar. If I take 2 as common, I'll get omega e bar minus 2 into v plus 1 into xc into omega e bar. What is this? This is the energy gap. This is the energy gap between adjacent level. Formula for energy gap. Students, observe carefully. In the case of simple harmonic oscillator, we found that energy gap is just omega e bar, correct? In the case of simple harmonic oscillator, energy gap is just omega e bar. It is independent of vibrational quantum number, I told you. In the case of simple harmonic oscillator, energy gap is independent of vibrational quantum number. Okay, that's why for all transition we get same energy of radiation is absorbed, right? We expect only one line in the spectrum, right? Whereas in the case of anharmonic oscillator, see this, the delta G between adjacent, now it has V. It has V, vibration quantum number is there. Therefore, depending upon the transition, the lower vibration level of the transition, you will get different energy required for the transition. For 0 to 1 transition, you will get some energy is required. For 1 to 2 transition, we put V equal to 1 here, you will get a different energy. So now the energy required for transition is not constant for all transition. Okay, take two. Students, up to this clear? Any doubt? If you find any difficulty, you please tell me. I'll wait for a few minutes. Hello, students. Is this clear?
Yes, sir.
Take down. Remember these formulas. Very, very important. Okay, what is the energy required for adjacent gap? Energy gap between adjacent level in the case of anharmonic oscillator. Xc is called anharmonicity constant. Omega e bar is the equilibrium vibrational frequency of the bond. V is the vibrational quantum number. Okay, actually speaking, this equilibrium vibrational frequency is applicable only for lower vibration level. If you go to higher vibration level, there is a small deviation in the equilibrium vibrational frequency, but the deviation is very small, so usually we neglect that. So if you write omega e bar, nothing wrong in it. Okay, but if you want very accurate calculation, then you have to use the relation appropriate relation for omega e bar. Okay, right. Now students, observe carefully. What I am trying to say here is, listen, what happens if V increases, students? If V increases, what will happen? From this relation, you tell me what happens if V increases.
Gap decreases.
Yeah, energy level gap decreases, correct? Okay, so let me show that in the next page. See, so in the vibrational energy plot, let me draw like this. Okay, for the anharmonic oscillator. Okay, so here we have energy, here we have X. Okay, this is X equal to 0. Students, observe carefully. This is the lowest vibration level, V equal to 0. And you know very well, the energy for this is nothing but 0 point energy of the molecule. And the next level is V equal to 1. Next level is V equal to 2. Next level is V equal to 3. Next level is V equal to 4. Like that, as we go above and above and above, what will happen? The levels comes closer and closer, right? Exactly at this place, above this place, right? Are close to the dissociation region, right? The vibrational gap become continuous, or the vibrational energy become continuous, and this V where dissociation occurs is called V max. Students, note down the highest vibrational energy above which the molecule dissociate, or at which the molecule dissociate. V max is the value of the vibrational quantum number at which the molecule dissociate. Okay, that's the maximum quantum number possible for the molecule, vibrational quantum number. Okay, so what does this indicate? This indicates that as you go above and above and above, the adjacent level gap decreases, and near the dissociation, right, the gap almost there is no gap actually. There is no gap, right? The levels actually merge each other, right? Students, observe carefully here. What is this? Student, what is this?
Equilibrium.
Equilibrium dissociation energy of the molecule, am I right? Students, listen. If I pass radiation of appropriate frequency, the molecule can move from here to the highest Vmax level, correct? If I pass some high energy radiation, then molecule will move from 0 to here. Molecule may be here, or maybe here, or maybe here. Molecule never be at this point. Okay, so suppose if molecule present here, then if I pass radiation, molecule absorb the energy here and dissociate. I can find this equilibrium dissociation energy directly from spectroscopy. Students, observe this carefully. Suppose if molecule is present at this point, okay, if I pass appropriate radiation, then molecule absorb the energy and goes here, and we can find the dissociation energy from the spectroscopy or from the spectrum itself. But this is the lowest energy possible for the molecule. So molecule may be, most of the molecule may be here or here or here, like that. Molecule never be here. Therefore, if I pass radiation, if molecule absorb energy from here and reaches this maximum limit and dissociate, you will get dissociation energy that is called spectroscopically measurable dissociation energy, which I am going to say that this gap, I am going to represent this as D0. What is D0? D0 is nothing but spectroscopic dissociation energy of the molecule. Okay, if I pass radiation, molecule absorb radiation from here and goes here. Once the molecule reach here, the molecule dissociate. That is also dissociation energy, but that is spectroscopic dissociation energy, spectroscopically measurable dissociation energy. Okay, spectroscopic dissociation energy of the molecule. What is DE? Equilibrium dissociation energy molecule, which we cannot measure through spectroscopy. But we know very well quantum mechanically. What is this gap, student? Anyone? What is this energy? What is this energy?
0 point energy.
That is 0 point energy. So this gap is nothing but 0 point energy of the molecule, right? So if you know 0 point energy quantum mechanically, and if you this you can find through experiment. D0 you can find through experiment, and if you know 0 point energy of the molecule through quantum mechanics, then if you add the two, you will get DE. So equilibrium dissociation energy equal to 0 point energy of the molecule plus D0. Take down. Students, I repeat once again. Through spectroscopy, you can determine only this. Only D0 can be obtained through spectroscopy. D equilibrium or equilibrium dissociation energy you can calculate by adding 0 point energy value to this. Okay, students, is this clear? Any doubt? Hello, students?
Yes, sir.
No.
Yes, no. Take down. Students, can you tell me which electronic state is this? For a diatomic molecule, this is actually an electronic state. Which electronic state is this?
Ground electrons.
Ground
electrons.
Yes, don't forget that. Don't forget that all these vibrational transitions we take in the ground electronic state. It corresponds to the ground electronic state of the molecule, right? So this dissociation energy, spectroscopic dissociation energy, equilibrium dissociation energy, these are all correspond to the ground electronic state of the molecule. Why I am telling this? You can also have dissociation energy for the excited electronic state also, okay, which is very useful in the case of photochemical studies, right? For photochemical studies, excited state dissociation energies are very important. Okay, we are going to learn that under electronic spectroscopy. For vibrational spectroscopy, we consider only the ground electronic state dissociation energies. Okay, so this is dissociation, equilibrium dissociation energy correspond to ground electronic state of the molecule. Take 2. Equilibrium dissociation energy correspond to ground electronic state. Okay, usually we put a double prime here. Double prime indicate ground electronic state. Okay, take 2. Now, students, observe carefully. So I have given the formula for G and delta G, right? Suppose if I want equilibrium dissociation energy, students, observe carefully. If I want equilibrium dissociation energy, how to calculate that? If you find the value of Vmax, Vmax is the vibrational quantum number at which the molecule dissociate, or above which the molecule dissociate. We can say it like that. Correct. So if you know what is the value of Vmax, then if you substitute that Vmax in the energy formula, students, are you able to follow this? See what I am trying to say? You find out the value of Vmax, okay, and substitute that Vmax here. What we get? If you substitute that Vmax here, what we get? What we get is the vibration energy for Vmax level, correct? What is the vibration energy for Vmax level? Vibration energy for Vmax level.
Dissociation.
That's all. That is nothing but equilibrium dissociation energy. So what I am trying to say is that, listen, the point is this. See, when V equal to Vmax, when V become Vmax, okay, then the G value, that is G Vmax. What is G Vmax? Vibrational energy at V equal to Vmax, right? Vibration energy at the maximum value of V will give you the equilibrium dissociation energy of the molecule. Simple. Okay. And remember, student, we calculate GV is nothing but vibration energy in wave number, right? Here I put just DE. I'll put a DE tidy here, which means equilibrium dissociation energy also you will get in wave number. Okay, you know very well. DE is nothing but C into DE bar. Simple, right? Equilibrium, I'm saying HC. Right? This is dissociation energy in joule. This is dissociation energy in wave number units. That's all. Okay. So now, how to find the value of Vmax? That's the question. If you know Vmax, yes, you can calculate DE. Right? How to find the value? Very simple. Students, observe carefully. As we go above and above, what happened to the gap? As we go above and above, what happened to the gap?
Decreases.
Okay, delta G, correct? Delta G decreases, am I right? Here we have large delta G, here delta G is small. So as we go above and above, delta G decreases. Near Vmax, what will happen to delta G? It becomes 0, right? Delta G decreases and becomes 0. So you can find Vmax very easily. How? Listen, to find Vmax, see, very easy. If delta G, you calculate delta G, right? If V approaches Vmax, delta G will become 0. Am I right, student? Am I right? If V approaches V max, delta G becomes 0. Is it correct? Yeah. What is the general expression for delta G? We derived it. What is the general expression for delta G?
V plus 1 by 2.
No. Delta G ma omega E bar minus 2 into V plus 1 XE omega E bar. Am I right? Am I right, student? We derived it, right?
Yes, right.
Yeah,
Yes,
this is the general expression for delta G. But listen, when V become V max, delta G become correct. See, if you don't put V max here, it is just a delta G formula. When delta G becomes 0, when V is V max, correct?
Yes, sir.
Yeah. Now listen, student, how to find the value of V max? Okay, I'll bring this term to the right hand side. So omega E bar equal to 2 into V max plus 1 into XE into omega E bar. I'll bring this 2 XE omega E bar to the left hand side. So I can write V max plus 1 equal to omega E bar you can cancel, so you'll get 1 here. Okay, so 1 by 2 XE. Is this clear, student? Any doubt? Or I can write V max equal to 1 by 2 XE minus 1. Students, is this clear? Hello students, is this clear?
Yes, sir.
Yeah, so if you know V max, you can find V max easily. How? If you know the value of XE. What is XE, student? What is the value of XE? What is XE?
0.0.
Yeah, XE value is roughly 0.01, right? Roughly 0.01 for most molecule, right? It is in the range of 0.01. I won't say that exactly 0.01. It may be around that value. What is XE actually? What is XE? Unharmonicity constant. Unharmonicity constant of the molecule, which is a constant for a given molecule. It's a constant for a given molecule. Okay. Suppose just for problem sake I'll say, suppose XE is say 0.01. What's the value of Vmax? Anyone? 1 by 2 into 0.01 minus 1. Can anyone tell me what's the value of this? This you can write to 10 power minus 2, am I right? When 10 power minus 2 comes to numerator, can anyone tell me the value now?
49.
49. What is that? What does that indicate? What does
Vmax maximum.
yes.
Vmax.
Is somebody is
49 level varaikkum pogudu.
Somebody is listening song also. Okay. Yeah, you'll get parallax error in the mind. Students, while attending class, your full concentration should be here. Okay. Yeah. Yes. So when molecule reaches 49th vibrational state, the molecule dissociate. Correct? Okay, so you can find Vmax using this formula. Students, observe carefully. Sometimes they will ask, they'll give the value of Xe, they'll give unharmonicity constant value, and they'll ask you to calculate Vmax. Okay, now so yes, you can find the value of Vmax using this formula. If I substitute this Vmax in the vibration energy formula, I will get the equilibrium dissociation energy. Correct? Okay, so what is our goal? The next goal is this. See?
Sir?
Yes.
Sir, if Vmax is 49, is this constant for all molecules, sir?
No, it is not. That's why I told you. Suppose if X equal to 0.01, for some molecule it may be 0.01 for one particular molecule. For another molecule it may be 0.099 something. Correct? Close to 0.01. Okay. Like that. So. But
mostly it will be same 0.01 for most molecules. Is same, sir?
No, it is in the range. Observe carefully. It is not constant for all molecule. It is a constant for a given molecule. I have told you, no? unharmonicity constant is a constant for a particular molecule, but the value will be in this range, close to 0.01.
Okay.
Okay, yes ma'am.
Okay.
So depending upon the value, it may be in some case the value may be 50 or 51, like that. Okay, Vmax value. It depends on the molecule, purely on the molecule.
Okay.
Yeah, right. But the Xc value is in the range of 0.01. That's the point you should keep in mind. I'm not saying that 0.01 is the value for all molecule. No. Okay, the range will be in this close to this. Okay, now when V become Vmax, students observe carefully. When vibrational quantum number become Vmax, okay, then GVmax. What is GVmax? Student, what is GVmax then? GV
is
DE, correct? Equilibrium dissociation energy in wave number unit. Am I right? Is this clear? Is this clear?
yes, sir.
Yeah. So DE equal to, see, what is GV formula? You know very well. V plus, wherever V is there, I'll put Vmax. V plus half into omega E bar minus V plus half the whole square into Xc into omega E bar. You know this formula. Okay, now wherever Vmax is there, you put 1 by 2 Xe minus 1 there. So if I put 1 by 2 Xe minus 1 plus 1 by 2 omega E bar, because you know very well Vmax value is 1 by 2 Xe minus 1. This we know. So wherever Vmax is there, you put that value here. Minus here also you put 1 by 2 Xe minus 1 plus 1 by 2 the whole square into Xe into omega E bar. So what we get is 1 by 2 Xe minus 1 by 2 into omega E bar. Okay, here also you will get 1 by 2 Xe minus 1 by 2 the whole square into Xe into omega E bar. Okay, students, up to this any doubt? Up to this any doubt, students? Just go through this carefully. So if I simplify this, what we'll get is let me simplify this further. So omega E bar, I'll multiply with omega E bar by 2 Xe minus omega E bar by 2 here minus this we have to expand this a minus b whole square. So a square 1 by 4 Xe square plus b square is 1 by 4 minus 2ab. So if you multiply by 2, 1 to cancel, so you'll get 1 by 2 Xe into Xe into omega E bar. Okay, students observe carefully. Xe value will be in the range of 0.01. I told you, right? Xe square means if Xe is 0.01, what is Xe square? 0.0001, correct? 3 zeros will come, correct? So this is negligible, become very small. So Xe square is negligible, right? So sorry, denominator quantity is negligible. Okay, that's the meaning, right? Anyway, let me keep it as such. We will see later. Now omega E bar by 2 Xe, I'll keep it as such, minus omega E bar by 2. Now I'll multiply this here and I also multiply with minus 1. So minus 1 into, if I multiply here, Xe, 1 Xe square cancel, Xe in the numerator and Xe square is there in the denominator. So Xe cancels, you will get one more Xe in the denominator, right? So you will get omega E bar by 4 into Xe, and here minus Xe omega E bar by 4, and here minus of minus become plus. If you multiply this, XE cancel, get omega E bar by 2. Is this clear, student? Any doubt? Any doubt here? Observe this carefully. Any doubt, student? I just expanded it, that's all. I just expanded formula. Now this and this cancel, right? Students, am I right?
Yes, sir.
Yes, sir.
Then see these two, I can simplify these two. How? Here 2xc, here we have 4xc. So 4xc is the LCM. So you'll get 2 omega E bar here minus omega E bar. So you'll get omega E bar minus xc omega E bar by 4. Take down. Omega E bar by 4xc minus xc omega E bar by 4. This is what we get. Take down. Is this clear, student? Any doubt? Hello?
No, doctor.
Yes, take two. So this will give me the equilibrium dissociation energy of the molecule. Okay, take down. Yeah, so we can calculate the equilibrium dissociation energy of the molecule using this formula. Or if I take omega E bar as common, I'll get D equal to, I'll take omega E bar as common. So what we'll get is 1 by 4xe minus xe by 4. Okay, take down. Students, xc value is in the range of 0.01. I told you. If I divide this by 4, it will become even small, right? Even small. Okay, 2, 5, like that goes. It becomes very, very small. So this term shows negligible contribution. It is negligible. So I'm going to neglect that. So you'll get dE equal to omega E bar by 4xe. Is this clear, student? Because this part will contribute only 0.002. If you want accurate calculation, you can use this formula. For accurate calculation, you can use this formula, right? But xc value by 4, it is very, very small, 0.02. It is in the range of 0.025 something. So you can neglect that. Okay, and you will get this value. And we write this formula like this because for convenience. Omega will multiply both numerator and denominator by omega E, so you'll get 4 omega E bar xe. We write like this because, okay, for our convenience. I'll tell you why we multiply both omega E bar in the numerator and denominator. I'll tell you. because when we take spectroscopy, when we take spectrum, from the spectrum result, okay, you will get the omega e bar square, omega e bar xc directly, so you can easily calculate. This is for calculation purpose we are using this formula, right? Remember this. So you can calculate the equilibrium dissociation energy of the molecule. Is this clear, student? Is this clear? Any doubt? Students, is this clear?
Yes, sir.
Yes, sir.
Yeah. So we have discussed about the vibrational energies, equilibrium dissociation energy, right, and the spectroscopic dissociation energy, etc., etc. See, once you know these values, omega e bar, x e bar, omega d value, if you know all these value, you can calculate d0, right? d0 bar. How? Spectroscopic dissociation energy. How will you calculate this?
Sir, கீழ இருக்க ஃபார்முலா எப்படி சார் வந்தது?
I just multiplied the numerator and denominator by omega e bar.
Okay, sir.
If you multiply numerator and denominator by omega e bar, we'll get this. See, student, this relation is very important relation because once you solve the spectrum result, you will get omega e bar xc value directly. Okay, you need not find the xc from that. Just put omega e bar xc bar value directly and omega e bar square directly. You'll get the equilibrium dissociation. That's all. Okay. This is for problem sake we are using this formula. Otherwise, this is the formula. Okay, and this is the accurate formula. Remember, this is the accurate one. Okay, am I right, student? Is this clear? Now, what is D0?
Yes.
D0 is nothing but equilibrium dissociation energy minus 0 point energy. Am I right? If I subtract 0 point energy from DE, I'll get D0, correct? So you can find DE from this equation, and if you know 0 point energy, you can, if you subtract that, you will get the D0 value. You can also get D0 value through spectroscopy. Okay, you can compare whether the two values correct or not. Yeah. Okay, now students, any doubt up to this? Students, any doubt?
No, sir.
Are you comfortable?
No, sir.
Are you comfortable with this? Yeah, these relations are quite simple, but very, very important. So it is it requires some practice. So you need to write and practice everything. Now let's do the next one. Selection rule. Take two. Selection rule. We talked about the vibrational energies, okay, dissociation energy, etc., etc. Now we are going to focus on selection rule. Students, as usual, here also we get two selection rule. One is gross selection rule. Gross selection rule for anharmonic oscillator. What is the selection rule? The selection rule is this. That is dipole moment, permanent dipole, not permanent, I'm sorry. Dipole moment of the molecule should change during vibration. Okay, not equal to 0 means it is changing. Dipole moment of the molecule should change during vibration. That is the gross selection rule. What about the specific selection rule? Specific selection rule, which we can obtain by from quantum mechanics by finding transition moment integral. Okay, which I'm not going to do here. I'm going to give you the final result. Right, the specific selection rule says that delta V, change in vibrational quantum number, should be plus or minus 1, plus or minus 2, plus or minus 3, etc., etc. All these transitions are allowed. See, in the case of simple harmonic oscillator, only this transition will appear in the spectrum. Okay, delta V plus 3 does not appear, I have told you, because the integrand value is very, very small. Whereas in the case of anharmonic oscillator, all these transitions are very well allowed, and all the transition will appear in the spectrum. Okay, now listen, student, what is the meaning of this? Okay, see, let me ask the question. V equal to 0 to V equal to 1. Is this transition allowed? Students, is it allowed?
Yes, sir.
Yeah, final number is
sir.
plus 1, initial number 0. So delta V is final minus initial plus 1. Yes, it is allowed. V equal to 0 to V equal to 2. Is this allowed?
Yes, sir.
Yeah, final number is plus 2, 0. Yes, difference is 2. Allowed. Okay, so like that you can find which are the transitions are. Here almost all transitions are allowed. Right, all transitions are allowed. Plus signs indicate is applicable for absorption. Minus sign is applicable for emission. Now, students, observe carefully here. Let me write to the new page. Observe this. So, in the case of anharmonic oscillator, right? So, this is the potential energy function, Morse potential energy function. Okay, Morse potential energy function, and these are all the allowed vibration level. V equal to 0, V equal to 1, V equal to 2, V equal to 3, right, etc., etc. Like that, many levels. Students, observe this carefully. 0 to 1 transition. Is this transition allowed?
Yes, sir.
Yeah, this transition is allowed, and this transition is called V equal to 0 to V equal to 1 transition is called fundamental vibrational transition. It is called fundamental vibrational transition. Fundamental vibrational transition. 0 to 1. Okay, and this transition 0 to 2, is this allowed? Students, is this transition allowed?
Sir.
Yes, sir. Yes, sir.
Yes, 0 to 2 also allowed, and this transition is called first overtone transition. First overtone transition. Okay, what about 0 to 3? Is this allowed?
Yes, sir.
That is also allowed. V equal to 0 to V equal to 3 is also allowed, and this is called second overtone transition. Second overtone transition. I'll just put OT. Second overtone transition. Similarly, V equal to 0 to V equal to 4 is called third overtone transition. Right? 0 to 1 is fundamental. 0 to 2, 0 to 3, 0 to 4, 0 to 5. These are all called overtone transitions. All these transitions are allowed and they appear in the spectrum. And see, student, this is very important. This transition is very important. See here, this transition. Is this transition allowed, student?
Yes, sir.
1 to 2. Yes, it is allowed. But students, listen carefully. The vibrational gaps are usually large compared to rotation, compared to translation, right? Compared to translation, rotation, the vibrational gaps are very large. Therefore, at room temperature, right, at room temperature, most molecules are present in V equal to 0 level. Okay, so if 0 to 1 transition takes place, many molecules will participate. So you will get intense line in the spectrum. 0 to 2, yes, many molecules participate. So fundamental transition, overtone transition, right, they appear with some good intensity. But in V equal to 1 level, at room temperature, the population in V equal to 1 level is very poor. Usually less than 1% will be there, less than 1%. Therefore, even this transition takes place, the transition does not appear with good intensity. The transition does not appear with good intensity. So, to make this transition appear in the spectrum, what we have to do? Students?
Increase temperature.
Vary temperature.
Very good. Why? If you increase temperature, right, many molecules will go to the higher vibration level, correct? Many molecules will go to higher vibration level. So, student, as temperature increases, right, as T increases, population in V equal to 1, V equal to 2, etc., okay, increases. So now population in V equal to 1 will increase. Therefore, if transition takes place from 1 to 2, now that transition will appear with a good intensity. That's why this transition V equal to 1 to 2, right? It appears only under hot condition, so it is called hot transition. It is called hot transition, first hot transition. V equal to 2 to 3. V equal to 2 to 3 will appear with still higher temperature, correct? Am I right, student? Because V equal to 2 level population compared to V equal to 1 level, 2 level population will be very, very poor. If we heat the sample to a larger extent, yes, molecule will go there, then the lines will start to appear, correct? So it is called second hot transition. Second hot transition. Like that we have third, fourth, etc., etc. Students, are you able to follow this? Any doubt? Hello, students?
No, sir. No, sir.
No.
Okay, so keep this in mind. Why these transitions 1 to 1 to 2 to 3 are called as hot transitions? What's the reason? Why these transitions are called as hot transitions? Hot?
Higher temperature transition.
Higher temperature.
These transitions are their signals will appear in the spectrum only under hot condition. Because only under hot condition, molecules will reach V equal to 1 level. Molecules will reach V equal to 2 level. Then only many molecules participate in their transition, so you will get intense signal in the spectrum. Okay, so that's why these transitions are called as hot transitions. So students, this is a very important one. So initially molecules are here. As an increased temperature, what will happen? As an increased temperature, slowly molecule will go here, slowly molecule will go here, slowly molecule will go here. At one stage molecule will reach here, correct? Vmax. If molecule reaches Vmax, what will happen?
Dissociate.
The bond rate
Equilibrium.
Students, observe, this is very, very important. Why molecule dissociate on heating? Why does molecule dissociate on heating?
Bond breakup.
Very good. As you heat, as you supply heat, what will happen? Molecule goes to higher vibration level. So amplitude of vibration will increase, correct? If molecule goes to higher vibration level, amplitude of vibration increases. When molecule reaches Vmax, the bond will dissociate. So that is why, right, we say that molecule dissociate under hot condition or under high temperature. That's the reason. Is this clear, student? Is this clear? Hello?
Yes, sir.
Okay. So student, this is the point I like to say here. DE, what is DE? I'll put DE double,
dissociation.
I'll put DE double prime. What's the meaning of DE double prime? Anyone?
ground state electronic
Ground
charge.
state.
Clearly, say clearly.
Ground state equilibrium constant for dissociation energy, sir.
Absolutely wrong. Say clearly.
Equilibrium dissociation energy corresponds to ground electronic state.
Excellent. Equilibrium dissociation energy corresponds to ground electronic state. This you can find thermally also, correct? Can we find this thermally?
Yes, sir.
Yeah, in 12th standard, somewhere you might have heard about this bond dissociation energy. In thermochemistry, you might have heard about this. In thermochemistry. Correct? Yes, thermally you can find dissociation energy. Nothing wrong in it. You can calculate. Equilibrium, the dissociation energy for the ground electronic state, you can determine through thermal methods, thermochemical methods. Using thermochemical methods, but the value is not so accurate. Using spectroscopy, we can determine only D0. Spectroscopic methods. Okay, and using spectroscopy and other technique, you can calculate this DE. Right, and by finding the 0 point energy, you can calculate this. Okay, so remember, this is the point I like to say. Equilibrium dissociation energy for the ground electronic state can also be obtained by thermochemical method, but the value is not so accurate. Okay, is good, the value is good, but compared to other method it is somewhat less accurate. Is this clear, students? Hello?
Yes, sir.
Okay, sir.
Yeah, so I have given the selection rule and I have given the possible transitions. What is meant by fundamental vibrational transition, first overtone transition, second overtone transition, hot transitions, etc., etc. Okay, and you also know what is the energy required for transition. Okay, what is the energy required for transition, student? What is the energy required for a transition? I'm sorry. Yes, that's the we need to discuss. What is the energy required for a transition? We cannot give a general expression here. We cannot give. Why? Because 0 to 1 is allowed. 0 to 2 also allowed. 0 to 3 also allowed. So we cannot give a general expression here. I'm going to give the energy required for transition for each and every transition separately. 0 to 1 transition is called fundamental transition, am I right, students? 0 to 1 transition is called fundamental, correct?
Yes, sir.
For fundamental transition, what is the energy required? What is the energy required for a fundamental transition? Delta G equal to, so you know very well the formula for delta G. Let me rewrite that, or I'll do one thing. What is G formula? GV equal to V plus half into omega E bar minus V plus half the whole square into XE into omega E bar. Okay, so this is the formula for vibration energy in wave number unit. Okay, now 0 to 1 transition, what's the delta G? That is the energy required for transition, is nothing but vibration energy for the higher level minus vibration energy for the ground level. 0 to 1. Okay, also called fundamental vibrational transition. Also called fundamental vibrational transition. So what is the energy required for a fundamental vibrational transition? I'll put like this: fundamental vibrational transition, FVT. Energy required for fundamental vibrational transition. Okay, so if you put 1 here, wherever V is there, you put 1. So I'll get 1 plus 1 by 2 is 3 by 2. So 3 by 2 omega E bar minus, if I put 1 here, I'll get 3 by 2 square, which is 9 by 4 XE into omega E bar. This is the vibration energy when G equal to 1. If I put G equal to 0 here, V equal to 0, then half omega E bar minus, if I put V equal to 0 here, 1 by 2 square is 1 by 4. So 1 by 4 XE omega E bar. Okay, 3 by 2 minus 1 by 2, I'll get omega E bar. And minus 9 by 4, this become plus 1 by 4. Minus 9 by 4 plus 1 by 4 will give me 2. So minus 2 into XE omega E bar. Or if I take omega E bar as common, omega E bar into 1 minus 2 XE. Students, this is the energy required for fundamental vibrational transition. Take down. Energy required for fundamental vibrational transition, omega E bar into 1 minus 2 XE. Energy required for fundamental vibrational transition. 0 to 1 transition is called fundamental vibrational transition. So if you know omega E bar, if you know anharmonicity constant, you can calculate this value. You can also calculate these values from the spectrum. We'll discuss that as we go along. Now, what is the energy required for 0 to 2 transition? What is this transition called, student? What is this transition called?
Overtone transition, sir.
Is it just
First
overtone or
overtone.
first overtone?
First overtone.
Yeah.
First overtone.
So what is the energy required for first to overtone transition, FOT? Is equal to energy of the higher level 2 minus energy of the lower level, which is 0. Correct? What will get? Anyone? Just use this formula and find out the value. Tell me the final answer. Tell me the final answer. This part remains same. Okay, you have to find out only this part. Put V equal to 2 there. 2 means 5 by 2 omega E bar here, 5 by 2, and here if I put 2, 5 by 2 square is 25 by 4 XE into omega E bar. So 5 by 2 minus 1 by 2, I'll get 4 by 2, 2 omega E bar minus 25 by 4 minus 1 by 4. Yes, student? Very easy. Just check it whether you get this answer or not. 2 omega E bar into 1 minus 3xe. Students, please check and tell me. For first two overtone.
Yes, sir.
2 omega E bar into 1 minus 3xe you will get, okay? Similarly, if you go to second overtone transition, let me write here.
Sir,
Yes?
so we have our next class by 11. Sir.
11, huh? Okay,
yes,
then I
sir.
stop here, ma. Then I stop here. Just I'll give this value and stop. For 0 to 3 transition, that is second overtone transition, we get the value as 3 omega E bar into 1 minus 4xe. And for hot transition, that is first hot transition 1 to 2. 1 to 2 transition is called first hot transition. First hot transition FST is equal to, you will get 1 by omega E bar into 1 minus 4xe. Okay, you just do the calculation and check whether it is correct or not. Okay, take down. So this is the energy required for fundamental, this is the energy required for first overtone, energy required for second overtone, energy required for first hot. Okay, remember all these values. All these expressions are very important and you should remember. Take down, student. Okay, I stop here. We'll continue the next class.